A 1000 kHz carrier is simultaneously DSB-SC modulated with 300 Hz and 2 kHz sinusoidal waves. Which one of the following frequencies will not be present in the output? He clearly mentioned system is DSB-SC. So, in the system, we are suppressing the carrier. So, here double-sided band, that means upper side band and lower side band. In the system, we have the frequencies of upper side band and lower side band. Here he mentioned carrier frequency is FC equal to 1000 kHz and FM1 equal to 300 Hz, FM2 equal to 2 kHz. So, we know that in DSB-SC system, the output frequency components are FC plus or minus FM1, FC plus or minus FM2. So, here he clearly mentioned 1000. So, 1000 kHz plus or minus 300 and 1000 kHz plus 2000 Hz plus or minus. So, here 1000.3 kHz and we need to subtract 300 Hz from this 1000. So, that is 999.7 kHz. Here this is 2 kHz. So, 1002 kHz and if you subtract 2k, this is 998 kHz. So, from the given options, option A is 998 kHz is present, option B is 999.7 kHz, it is also present, option C is 1000.3 kHz, so this is also present, option D is 700 kHz. So, our answer is the option D. In a broadcast super heterodyne receiver having no RF amplifier, the loaded Q of the antenna coupling circuit is 80. If the intermediate frequency is 455 kHz, then the image frequency at the 1000 kHz. So, the Q value of the antenna is unnecessary here. Here we need to find out image frequency. He given intermediate frequency Fi equal to 455 kHz. Okay. And incoming frequency Fs equal to 1000 kHz. So, we know that image frequency here by default we need to consider Fl is greater than Fs. So, in this case we know that image frequency Fs plus 2Fi, that is 1000 Hz plus 2 into 455, that is 19110 kHz. So, from the given options, answer C is the correct one. Ready. Consider a telephone quality speech signal, the width of the frequency having null values. Here he clearly mentioned this is telephone quality speech signal. So we know that telephone signal occupies from frequency spectrum is from 300 Hz to approximately we are taking 3.5 k kilohertz. So this is one. So here negative frequency also like this. Let us consider only this frequency. So this is minus 300. This is minus 3.5 kilohertz. We need to find out the width of the frequency having null values. If you modulated this signal, it is shifted like this. So this is FC plus 300 Hz and FC minus 300 Hz. Here FC plus 3.5 kilohertz. Here FC minus 3.5 kilohertz. So here we need to calculate the null space. So this is the null space. This is FC plus 300 minus FC minus 300. So this is 600 Hz. So from the given options, answer C is the correct one. The Hilbert transform of odd signal will be. Here we need to find out Hilbert transform of a odd signal. So let us consider x of t of x cap of t is the Hilbert transform of the x of t. This is nothing but x of t convolution with 1 by pi t. So this is the Hilbert transform operator. So from this equation we can clearly say that this is odd signal. So we need to find out Hilbert transform of odd signal. So he mentioned that this is also odd signal. So we know that odd signal convolution with odd signal is even signal. Convolution is nothing but like a product operator. Odd signal multiply with odd signal is even signal. So from the options, answer is the option A. Thermal noise in an earth station receiver results in a carrier to noise ratio in the down C by N down equal to 20 dB. a signal is received from bent pipe transponder with a carrier to noise ratio with up. This is downlink, and C by N ratio of up equal to, if the transponder introduce intermodulation product with a carrier to intersymbol interference ratio is 20 dB. So what is the overall carrier to noise ratio at the receiving earth station? So we need to find out C by N overall. So here we know that C by N overall is the parallel combination of all these three. That is 1 by C by N naught overall equal to 1 by C by N up plus 1 by C by N down plus 1 by C by I. So here this is 20 dB is 100. Here it is also 100. It is also 100. N overall equal to, so are equivalent, and we need to find out parallel combination. So it will divide by 3. So we will get 33.33 is the overall C by N naught. So from the given options, answer is the C. The core radius required for single mode operation at 820 nanometer of a step index fiber with N1 equal to, that is refractive index of core is 1.480, and N2, that is refractive index of cladding is 1.478. The operating wavelength lambda equal to 820 nanometer. We need to find out A here. So here he clearly mentioned for single mode operation. So for single mode operation, the normalized frequency is, for single mode operation, V, that is normalized frequency, is less than 2.402. So we know that normalized frequency formula is 2 pi A by lambda into numerical aperture is less than or equal to 2.402. So we know that numerical aperture square root of n1 square minus n2 square. So from this, so we need to find out A. So here A should be less than or equal to 2.402 into lambda by 2 pi into numerical aperture is n1 square minus n2 square. So by substituting 2.402 into lambda is 820 nanometers to 10 power minus 9 by 2 pi into square root of n1 is 1.480 whole square minus 1.478 whole square root. That is, this is less than or equal to 4.07 micrometer. So from the given option, answer is the option B. Which one of the following formulas are correct when two amplifiers are connected in cascade as shown in below figure. This is the figure. This is gain G1 with noise figure F1. Here this is G2 gain F2. So here we need to find out what is the correct options from the given options. So we know that overall noise figure in terms of noise factors, that is F1, F2, that is F1 plus F2 minus 1 by G1, that is gain of the first amplifier. So it won't depends upon gain of the second amplifier. One more formula is there, noise figure in noise equivalent temperature, that is T suffix E equal to T1 plus T2 by G1, that is gain of the first amplifier only. It won't depend upon gain of the second amplifier. So from the options, overall noise factor F equal to F1 plus F2 minus 1 by G1. So this is correct. First one is correct. Overall noise equivalent temperature T equal to T1 plus T2 by G2. So this is wrong. Third one, overall noise factor F equal to F1 plus F2 minus 1 by G2. So this is also wrong. Here G1 is there. So one more is overall noise factor. We know that from the T equivalent T0 into F minus 1. So here F equal to TE by T0 plus 1. So the fourth one is overall noise factor F equal to 1 plus TE overall by T0. So this is also correct. So from the given options, 1 and 4 are correct. So option C is the correct one. A microwave link consists of a television antenna placed at a height of 169 meters and receiving antenna placed at a distance of 64 kilometers. Then find the height of the receiving antenna. So here he given height of the transmitter antenna is 169 meters. And receiving antenna is placed in the distance of 64 kilometers. 64 kilometers. And here we need to find out height of the receiver antenna. So this is the thing we need to find out. In this diagram, he clearly mentioned 64 kilometers is the line of sight distance. So we know that line of sight distance D equal to 4.12 into square root of HT plus square root of HR in kilometers. This is should be in kilometers. So here LOS distance is 64 kilometers. 64 equal to 4.12 to square root of HT is 169 meters plus square root of HR. So by substituting these things, we will get HR is nearly 7 meters. So the receiving antenna height should be 7 meters. Otherwise, we are unable to receive the signal from transmitter. So at least 7 meters of height of receiver should be placed here. So from the given options, answer is the B.